We're looking at 2007 Part A, question number 3. Let's see, an external direct current power supply is connected. That's really important, and so is this. What that is saying is it is supplying power. It's a battery or a wall socket or something like that. So right now we know that this is an electrolytic cell, and that's going to make some assumptions in this. One is that we know that E cell now is going to be negative overall. So that's a good thing to notice right off the bat. It's connected to 2 platinum electrodes. Hey look, inert electrodes. They are immersed in 1 molar copper sulfate solution, so that's the electrolyte in this electrolysis. As the cell operates, copper metal is deposited onto one of the electrodes. Ooh, that's a good piece of information right there. If it's deposited onto the electrode, it means that the half reaction that they've drawn up here in this box is actually the way the half reaction is going. Copper is becoming copper solid, and that's why it's depositing, and this electrode is getting bigger and bigger and bigger, thicker, more massive. So in any case, that gives us some good information. Now, let's look down at A. On the diagram, indicate the direction of electron flow in the wire. Well, let's think about this. If the copper reaction is being reduced, that means it has to gain electrons. So we know that the electrons are going that way, sort of counterclockwise. So that would be the answer to A. Boom, done. You notice it didn't really say if you should justify your answer. It would always be a good idea to do that. And so your justification would be, well, copper's being reduced, and the evidence for that is the electrode is getting bigger or more massive, and therefore electrons need to be flowing towards the copper. Then let's look at B. Write a balanced net ionic equation for the electrolysis reaction. Well, we know that the copper has to be as a reduction, and so therefore the top one can't be a reduction, so we're going to have to reverse it. The other thing is, you'll notice we're going to have to multiply everything in the copper reaction times 2, because it only has 2 electrons and the other one has 4. So I'm going to write, I'm not going to do B there. Let's do B down here where we have a little bit more room. So I'm going to write 2 Cu 2 plus, and you remember we're going to cancel the electrons anyway, so I'm not going to include those. Plus O2 plus 4H plus goes to, I made a mistake, didn't I? Let me go back. Boop, boop, boop. Well, let me go back. Remember the top one we got to reverse. So let's see, let me get my pen back here. And the top one we have to reverse. So we're going to have water, and 2 waters goes to 4H pluses plus O2 plus my copper metal. So I hopefully reversed the top reaction as we should have. And then you'll notice that when we add these 2 up, remember we're changing the sign of this one. And so when we add those 2 together, we'll get a negative value, which is what we said we should have had in the beginning. On to part C. Predict the algebraic sign of delta G for the reaction. Justify your prediction. You notice when they say prediction, usually they do not mean calculation, because they're going to have you calculate it in the next one. So I don't think it's simple and as simply as taking these 2 and figuring out the cell potential and justifying it that way. They want a prediction. So we're going to do that next part in D in just a minute. So in C, what would be a reasonable answer? Well, I would say that delta G is definitely going to be, well, it's a non-spontaneous reaction because it's an electrolytic cell. So delta G is going to be positive. And your evidence for that is the cell is an electrolytic cell. And energy is being supplied. To move the reaction in a non-spontaneous direction. I'm sure you can find a shorter way to do that, but the piece of evidence here is that it's an electrolytic cell. Then in part D, let's see, D, they actually want us to calculate it. And you know to calculate it, you're going to need to find out E cell. And for reasons that we said in part A, we need to reverse the voltage of the oxygen reaction. So it's going to be negative 1.23 volts plus positive 0.34 volts. And when we do that, E cell is going to equal negative 0.89 volts, as it should, because it's an electrolytic cell. It's negative. And then, of course, to convert cell potential to delta G, we need our old buddy Gunphy. And let's see, we know the cell potential. We know the cell potential, we know F, and we know N. N here is going to be 4 electrons, because you remember we had to multiply this second reaction times 2 to get it to have the same number of electrons exchanged as the top one. So it's going to be 4 electrons. I don't want to forget my negative. We're going to have 96,485 for Faraday's constant, and our cell potential is negative 0.89 volts. So when we calculate our delta G, it is going to come out to be 343,540 joules. Let's see if they specified units, by the way. Oh, also notice this came out to be positive, as we predicted up at the beginning, so it's always good to check. So it came out to be positive. We're going to check a few things here. One is, did they specify the units? No, they did not. So it doesn't matter whether it's in kilojoules or joules, but we also need to worry about sig figs. And you'll notice that this had 2 sig figs, that had a lot more. That's an exact defined number. So if I were going to answer it, I would answer it to 2 sig figs. And I actually think I'm going to make it a little bit easier. I'm going to say 340 kilojoules. And that should be my answer. Alright, we're down to E. E, they want us to calculate the amount of copper that gets deposited on the electrode if you have this many amps and that many minutes. Remember, minutes we need to change to seconds, and amps is coulombs per second. And this is a classic deposition question. We always start with time. So we have 40 minutes. We convert minutes to seconds. And then we use our current. We have 1.5 coulombs. I'm going to put in correct sig figs per second. And then we have 96,485 coulombs per mole of electrons. That's Faraday's constant right there. And then we got to convert moles of electrons to moles of copper, which is what they want. And so here, let's go back up and see how many electrons are exchanged here. You notice that 2 electrons are exchanged for every 1 copper. So I think that's what I'm going to do, 2 moles of electrons for every 1 copper. You could say, well, remember we multiplied all this by 2, but then you'd have 2 coppers for every 4 electrons. And you'll notice it won't make a difference. So it's up to you what you want to do there. And then lastly, we need to convert moles of copper back to grams of copper. And I believe the molar mass of copper is 63.54. And at this point, we're ready to calculate, and the answer comes out to be 1.19 grams of copper. And let's check sig figs. We had 3 sig figs there, there, and 3 sig figs there. So let's go with 3 sig figs, and that looks good. And then lastly, F. They want us to calculate the dry volume. Remember, that just means with no water in it, because there's water vapor in there. In liters measured, and they give you temperature, they give you pressure. It's starting to feel like a Pivnert problem. And they want to know how much oxygen was produced. And you remember that the first part was to figure out the stoichiometry of the reaction based on time and current. But once we know how much gets made, it's just a stoichiometry problem to find out how much of another substance gets made. So we know that during that amount of time, the amount of copper that got plated out was 1.19 grams of copper. And if we want to find out how much oxygen got made, it's simply a matter of starting with 1.19 grams of copper in our reaction and converting it to, well, not grams of oxygen because they didn't want that, but converting it to moles of oxygen. and then we can do PV equals nRT on it. So let's do that. If we do 1.19 grams of copper and we do the molar mass of copper, 63.54 grams of copper per mole of copper, and we're going to end up with 0.187 moles of copper. And then if we look at the mole ratio in our balanced equation, there were 2 coppers right here for every 1 of those oxygens. So if 2 coppers results in every 1 oxygen according to the balanced equation, then if I have 0.187 moles of this stuff, it'll result in half of that. So I don't know if I have that in front of me. Oh yeah, I do. It's 0.00933 moles of oxygen. And at that point, we can do PV equals nRT, and we know our N, we know RT, we know the whole thing, and we're solving for volume. So volume equals nRT over P, and I'm going this way because I'm running out of room. So volume equals our N, which was 0.00933, times, oh, I wish I'd left more room. I'm going to erase it. Yeah, I need more room. So we're going to do volume equals 0.00933. Alright, so we got interrupted by the Pledge of Allegiance there. So in any case, I scooted everything over, and you notice I have the moles that we calculated earlier. I have I have R, and you remember we used 0.0821 because that's the one we use in PivNert. I converted the temperature to Kelvin, and we can keep the atmospheres. It was nice of them to do that. And so now we can write down our final answer. So V equals, and it looks like the volume equals 0.197 liters of oxygen. And I shouldn't have boxed it before I checked sig figs. Let's do that. We calculated our mole amount from our gram amount up above, which we thought had 3 sig figs, so that should have 3. And our answer down here should have 3, so that should have 3. This is enough. That has 3, and that has 3, so I think 3 is a reasonable number.